All right, so using the formula, we apply the formula to this example. We now are guessing our A. I've got multiple guesses coming in, and 2 is correct. How do we tell? Because notice here, the A is the coefficient on the S. The negative is not incorporated into the A. So here we've got negative 2S, so that 2 right there is your A. And you can totally pull that out ahead of time as well. Now, in terms of this capital F part, that's the 1 over S minus 1. So it means we're trying to find the inverse Laplace transform of 1 over S minus 1. Anybody remember what that is? It's going to be an e to the t. Now, this answer right here of e to the t is f of t. We wanted f of t minus a. So what we're going to do is we're going to take that answer and replace all the t's with a t minus a. Okay? So this first bit right here turns into u to the t minus a. Our a was 2. Second bit turns into e to the t, but no, don't write the t. Instead of the t, we're going to write t minus a, so this would be raised to the t minus 2. Notice this substitution right here, where we replaced our t with a t minus 2. That t minus 2 came from your t minus a in the formula. And that's one of the reasons I would always recommend doing this scratch work. Here in this example, it was below. That way, you can just go ahead and use the straightforward rules from the inverse Laplace transforms. Or if you're using regular Laplace transform rules, that's totally fine too. Last step before you actually give your final answer, do that conversion where you're literally swapping out your t with your t minus a. And that's it. That's literally all you do with this guy. The only way that it can get a little bit more fancy is suppose you have something like this next example. Notice it's also going to be incorporating a discontinuous component. So you still have that e raised to the negative 3s. And then something else that's going to be that we're going to have to take the inverse Laplace transform of the other stuff. The first step I'd recommend doing is to go ahead and write it out. Specifically, split the e to the negative 3t out, not 3t, 3s out front, and then have the other bits after it. So what does this tell us? At this point, this tells us we have our step function, and we're going to have t minus a, whatever a is, and then we're going to have something else. Okay? So here, what's our a in this case? Anybody got it? Yep. Totally is going to be 3. So we'll have t minus 3 plugged in up there. And over here we'll have, well, this whole fraction. I'm going to go ahead and not try to cram that in. Plug in that whole fraction right there. And that last piece, once we find that inverse Laplace transform, we're going to replace all of the t's. Too tiny. With t minus a, our a was 3, so t minus 3. So now the problem breaks down to what is the inverse Laplace transform of this guy that's s minus 5 all over s plus 1 times s plus 2. And if you look at all of our rules, what we'll find is, well, that doesn't match with any of our rules. Ugh. Okay? So this is where when you have inverse Laplace transforms, you have a procedure. You should always have a fraction. If you don't, combine the appropriate terms to get a fraction. And we'll see what goes on in that sense later today. Once you have your fraction, you may have to do some algebra to put it in the correct form. Now, the algebra involved typically breaks down into 2 cases. One of them is completing the square, and the other is dealing with partial fractions. And the way you choose between completing the square and partial fractions is whether the denominator at the bottom of the fraction factors or not. So completing the square is when the bottom doesn't factor. Partial fractions is when the denominator does factor. So what do you guys think we're going to use here? Partial fractions or completing the square? Yep, we're totally going to use partial fractions. So in terms of using partial fractions, that's just an algebra step. So let me title this partial fractions. So we'd have our, pretend that was an s, minus 5 over s plus 1, s plus 2. And this would be something over s plus 1 plus something over s plus 2, standards, capital A, capital B. Then we go ahead and we'd solve for whatever that capital A and that capital B were. So here what we have, the standard is to do sort of cross multiplying. So first numerator, the s minus 5, then we'd have A times s plus 2, we'd have B times s plus 1. We'd plug in appropriate values. So maybe you plug in s equals negative 1. If you plug in s equals negative 1, we'll get A equals negative 6. Everything else cancels. And if we plug in s equals negative 2, the term with the A cancels, and you'll get negative B over there on the right-hand side. And on the left-hand side, the negative 2, the negative 5 gives you negative 7. So this tells you that B equals positive 7. So plug it in, and we'll get 7 over s plus 2 minus 6 over s plus 1. Okay? So I just plugged in. Now, what does that mean for us? That means that when we're trying to find the inverse Laplace transform, this is literally the same thing as the inverse Laplace transform of 7 over s plus 2 minus 6 over s plus 1. Don't overthink it. We just did a rule similar to this. The first one's going to be 7 times e to some exponent. The second one will be 6 times e to some exponent. Anybody have a guess on what the exponent is on that first e? Hint, there'll be a t in it. The key thing is, what's the coefficient? On the t in the exponent of the first e. So the first one would be negative 2t. And the second one here with the 1 would be negative 1t. That's it. Now, we wanted that guy because going back to the original formula that was dealing with our step function, what did we need? In this slot right here, we're going to plug in our inverse Laplace transform. So what we just found, this guy right here. But what's the caveat? We are going to swap out all of our t's with t minus 3s. Okay? So to finish off this problem, and to make it so we can see that top work, what are we going to have? Get past all of that middle work. We will actually end up with u of t minus 3, so step function that breaks it t equals 3. Your inverse Laplace transform we just found, it's 7 times e to the negative 2t minus 6 e to the negative t. And because all of that was multiplied by our step function, I went ahead and put brackets around the whole thing. And notice, instead of writing the t, I wrote blanks. I personally find it easiest when I'm copying down something to go ahead and just write it out, sort of talking to myself, hey, I've got this negative 2t, but instead of writing the t, put in the blanks. Why? Because we're about to replace the t's with t minus 3. So in those blanks, we'll have the t minus 3. This is probably a carryover from teaching algebra for too long. And that's it. If you want to simplify, go for it. And if you go ahead and simplify this guy, some people like to keep the step function out front, which is totally fine. And if you do, the only thing that would simplify is the exponents on the e. So this would be 7e to the negative 2t plus 6 minus 6e to the negative t plus 3. But both ways are perfectly acceptable answers. Okay. Questions make sense? Feeling kind of okay? Slightly. And that's it with the discontinuous guys. That's literally it. You break it up, you pull out the discontinuous part, you take the inverse Laplace transform of the other part like normally, and the only sort of cleanup at the end is you're going to multiply the discontinuous part of the step function out front, and you're going to swap out whatever t's you normally got from your inverse Laplace transform of your function, the other part function, with t minus a, whatever a is. That's it. All right. So for the rest of the day, we're going to look at what happens if we use these Laplace transform stuff in inverse Laplace transforms to solve differential equations. And we definitely won't finish that today. So let's at least get with what the method is. So first thing is you have to have a differential equation. Technically, you could probably do this without initial conditions, but all of our examples are going to have initial conditions, and it's pretty typical, it's normal to use initial conditions or have initial conditions. And we'll see why as soon as we get through the first example. Okay? In terms of the steps, once you have your differential equation, you're going to take the Laplace transform of both sides, all pieces, parts, terms of the differential equation. Next, what you're going to do is you're going to solve for the Laplace transform of your solution. So this will be the Laplace transform of y if y is the dependent variable. The last thing is, once you have what the Laplace transform of y is, you then take the inverse Laplace transform of whatever that expression is to get normal, regular, old y, or the actual solution. Okay? When you do those three-step procedures, your initial conditions will automatically be incorporated, and your final your final answer after step 3 will have no constants in it. Remember what happens with initial conditions. You solve for one specific solution. You have a unique solution. There are no constants left. So we're going to be getting 2 unique solutions for these guys. The only exception to that is, what if you didn't have enough initial conditions? Maybe you have some constants left hanging around. Same deal if you had no initial conditions, which we're actually going to avoid. But if you had no initial conditions, you could substitute in constants for what the initial conditions should have been, and that's how you'd build for your constants out to the answer in the just non-initial value problems. Now, one of the key hallmarks of a differential equation is you have derivatives. So there's a big property that we're going to need from previously. We've talked about it before, but we've never actually used it. So the property goes as follows. It says, suppose you have a function and you actually have the derivative of the function. Then it claims if you have the nth derivative of your function, you're going to have s times n times the Laplace transform of regular old function with no derivatives minus s raised to the n minus 1 times the initial condition where you plug 0 into the original function, then decrease the exponent on your s by 1, increase the derivative here when you plugged in 0, and you keep going till you get to the first term with no s's out front. Now, that's the general rule. Here's it specific to what we're going to see. Whoa, too many. So first thing is, let's go ahead and give ourselves a common symbols and notation. If you have the Laplace transform of y, in other words, the Laplace transform of the solution we're trying to find, it's common to call it capital Y, and then the variable now is s when you're in the Laplace transform. When you're looking at the Laplace transform of the first derivative, notice this is exactly that top formula, but applied to the first derivative. So n equals 1 here from the formula. So first derivative, n equals 1, you'll have s raised to the first power, the Laplace transform of your solution y, minus your first initial condition. And that's it. Notice this term has no s, so that's the first time you stop. Now if you want the second derivative, notice what will change. We're going to start off with an s squared. So here, with the second derivative, we'll have s squared. Again, still solution of the Laplace transform of the solution y. Then you're going to have 1 less on the exponent of s, so you'll have regular old s, and you'll have first initial condition. And then you have your next initial condition. Notice you're plugging in zeros all the time. So your initial conditions have to have the independent variable to be 0. If not, there's a fix, but we don't have enough time left in the semester to go over the fix. So if you're interested, it is in your textbook. And the last one I'm going to write down for us today is what happens if you have a third derivative. You can do the same thing for fourth derivative, fifth derivative. I just didn't write them down. Okay? So if you have a third derivative, what happens? You'll start with s cubed. You still have your Laplace transform of the solution minus, and then the next terms are s squared, s, and then no s. And notice your conditions, initial conditions here. You have 0 plugged in all of them, and they start off with regular solution, first derivative, second derivative. So it's very interesting here. Y with your initial conditions go with the one with the lowest derivative to the highest derivative. That increases, but your s's to the exponent starts with the highest exponent and goes down to no s's. Okay? So it sort of goes opposite each other if you think of it in terms of increasing, decreasing. And that's it in terms of the properties we're going to need. So let us look at an example. And the first example I've got prepped up for us is somebody that we would never really need to use Laplace transforms with. It's a nice homogeneous guy, constant coefficients. We could totally just use characteristic equation, use those roots to build the actual solution, plug in the values of the initial conditions, and it probably would be faster to do it that way. Instead, I'm going to, on purpose with our examples today, except for one of them, are all ones we could use method of undetermined coefficients on, or just homogeneous like this first one is. And I did it on purpose that way you could go and solve them the other way and verify that the solution we got today is actually correct. Okay? We're not going to have time to solve it both ways today in class or on Thursday, but I did that on purpose so you'd be able to verify it on your own outside of class if you were interested. All right. So let us label what we're doing. So we want to solve this guy. Step 1. The step 1 is we are going to take the Laplace transform of both sides of this differential equation. Now I'm going to do this in more steps than is probably necessary, but at least for the first couple of examples, I want to make sure that you're very comfortable with what we're doing. So when you take the Laplace transform of both sides, I'm going to be lazy and just put that scripty L on both sides of our differential equation. Don't overthink it. Next thing, the side with the y's, I'm going to break it up on the pluses and the minuses, all minuses. So here we have the Laplace transform of the second derivative minus the Laplace transform of the first derivative minus 2 times the Laplace transform of regular old y. Now, anybody have a guess on what the Laplace transform of 0 is? Don't overthink it. What should I write on that other side of equals? Yep, it turns out to be 0. A couple ways that you can think about that. One of them is simply the Laplace transform of any constant is that number over s. 0 over s simplifies to 0. Okay. Now, notice we still have the symbols for Laplace transform in 3 places, so we have to replace those 3 placeholders with what the Laplace transform actually equals, and this is why we wrote down the formulas right up top. Okay. So the second derivative formula, we're going to replace this guy, and it's going to be, actually, let me do it to the side. One of the things that I have found helpful is to go ahead and write your formula over to the side. Now, technically, we already have this formula. It is s squared times the Laplace transform of y minus s times y0 minus y prime of 0. Now, we actually know what those blanks are going to be. Y of 0, the first blank right here, is itself 0. And y prime of 0, also they're given, one of our initial conditions, is itself 2. So if we go ahead and simplify this guy, that first expression is simply s squared y minus 2. So that's what we're going to plug in. So s squared y minus 2. If we then look at the Laplace transform of y prime, we can use the formula again. And y prime is right up here, this second line. This is going to be s times capital Y minus y of 0. Well, we were given what y of 0 is. It's our first initial condition. So we go ahead and we plug in that 0. We simplify this expression, and we're going to get simply s times y of s. Don't overthink this. Okay? So I'm going to plug that guy in, s times y of s. And lastly, we have 2 times the Laplace transform of y. And notice you don't have any derivatives, don't overthink it. That's just the new symbol, capital Y. Some people, if you're actually building all of these formulas from scratch and don't have this reference right here, you'll actually want to go from the Laplace transform of y first and build down. So you'd actually write these in backwards or pull them bottom to top from your list. All right, so that was step 1. We take the Laplace transform. Now, step 2. we want to solve for that Laplace transform of the solution. In other words, we want to solve for that capital Y. Okay? So notice that's just some algebra. Not going to lie, this one here sometimes feels like the hardest part of the entire problem because this is where you got to worry about all those details from algebra. Okay? So we're going to solve for capital Y, which is right here. It's right there, and it's right there. So we're going to go ahead and group all those guys together. We've got an S squared capital Y. We've got a S capital Y. Notice I put the subtraction sign there. And the last one is -2 capital Y. Now we do have one term that does not have a capital Y in it. That's this -2. So you move that to the other side and just have a 2. So go ahead and factor out the capital Y, which will leave us with an S squared minus S minus 2 times capital Y. And if you have a situation where you actually have constant coefficients, so right here, where you could have on the associated homogeneous solution or associated homogeneous differential equation, or in this case, the actual homogeneous differential equation, you could have applied the characteristic equation. What you factor out here, notice, looks identical to the characteristic equation, except it's not the R's like we used before. Okay? That's always true if you have constant coefficients. If you don't have constant coefficients, which is the other time when the Laplace transforms are extraordinarily useful, this is not going to correlate to that at all. Now, we're almost ready. Next step is what the capital Y or Laplace transform of your solution equals. You'll divide. So this is simply 2 over S squared minus S minus 2. And that's it. Third step. Well, I did not want that one to be black. Third step is we're going to go ahead and use that capital F, not capital F, capital Y, to solve for the solution. So solve for your solution, which is the inverse Laplace transform of the capital Y guy that we just found. So Y equals the inverse Laplace transform of 2 over S squared minus S minus 2. Notice why we needed now both Laplace transforms and inverse Laplace transforms, because we're going to use them both. Now, when we're going ahead and trying to find the inverse Laplace transform, just like if you were only finding the inverse Laplace transform, what do you have to do? You check your rules to see if this guy looks like a rule. Hint, it's almost never going to look like a rule. Okay? So what you're going to have here is you're going to want to have something that is completely one fraction, like it currently is, but we're going to see in the next examples that's not always the case, and you might have to combine things together. But you want one fraction, and then you check to see, is it in the correct format right now, or do I have to do some sort of algebra? And just like with our last example, when we said, hey, what do we do in terms of the algebra? The common things you do are completing the square or partial fractions. Any guesses what you would do here, either completing the square or partial fractions, because that's not a standard form for our rules. Yep, that guy's totally going to be partial fractions because it completely factors. So I'm just going to write this down, that this step right up here, that guy needs to be in one fraction in order for everything to work out. And the nice thing right here is this guy totally factors. It's S something else. What is that? -2 plus 1? Do a quick double check. So here are denominator factors, which implies we're going to use partial fractions. Now, it turns out this is actually one of the examples that we did last time. Okay? We actually, at the end of last time, let me find it, we had 2 over S squared minus S minus 2. I actually think I gave it to you in factored form. So let me grab this one. It was this thing right here. Oh, we had to factor it then too. Okay? And we broke it up. We didn't do all the middle steps, but we went ahead and we said, hey, this guy, we were going to be able to solve for our A, we were going to be able to solve for our B, we would have plugged in -1, we would have plugged in 2, and we would have solved for these two guys. And we said, well, hey, that means it breaks up in this way. So that means we have this answer right here. So I'm going to copy some of that in the expression that we have for today. Not all of it because we already did this part. Whoops, that didn't come down to the spot we wanted. All right, so here's what we have. We have 2 over s minus 2, s minus 1. So we have a over s minus 2 plus b over s minus 1. So there's our partial fractions. So here we'll solve for a and b, and we got that a equaled, make sure I put a on the same spot I put it before, a equaled 2/3, b equals -2/3. So this tells us here that y equaled the inverse Laplace transform of 2/3 times 1 over s minus 2 minus 2/3 times 1 over s plus 2. Well, at that point, it's now in standard form, and we saw that last time this meant that our coefficients were going to be 2/3. This fraction turned into e to the 2t, and then the next guy had a coefficient of -2/3, and here we also turned into the format of 1 over s plus 1 was a format of e raised to the at, specifically e raised to the -t. And that, right there, this is your solution, this is your answer. Notice when you get your solution or your answer coming from Laplace transforms, there is no last step where you go and you incorporate in your initial conditions to solve for the unknown C1, C2 that you would have gotten. Instead, if you go back here where we plugged in the initial conditions at the very, very first step here, that's where we're incorporating in the initial conditions to get all of your coefficients right here all together with the actual function parts as well. And that's it. So that's the idea here. Now, notice it was probably way longer to use Laplace transforms to solve this particular initial value problem, but it shows you the procedure where you would be able to easily verify what the actual correct answer is. So let's do something that is a little bit more complicated. Not that much more complicated. The only thing that's really going to change now is the fact that we're going to have a non-homogeneous differential equation. In other words, the thing that these guys are designed for. Well, I lied. They're really designed for the discontinuous discontinuous functions that occur in your differential equation. So that's actually the next example after the one I'm about to show you. Let's see what would happen if we don't have a homogeneous differential equation. So this guy, again, it has constant coefficients. We've got the second derivative plus 6 times the first derivative plus 5 times the original function. On the other side of the equals, we have 12e to the t. We have 2 initial conditions since second order. So we've got at -1, and the derivative is going to be 7, both when t equals 0. So here, of course, you could do method of undetermined coefficients or variation of parameters. Both of them would work beautifully. Variation of parameters, probably going to be similar-ish in terms of the amount of work that you would do, maybe a little shorter. Method of undetermined coefficients, pretty much guaranteed to be shorter than what we're about to do, just because you have a guess involved. So step 1, we're going to go ahead and take Laplace transform of all the sides. So just like before, we take the Laplace transform of the side with the derivative. So Laplace transform of y second derivative plus 6 first derivative plus 5 fy. And then we now have a Laplace transform of something not 0. So this is the Laplace transform of 12 times e to the t. So this is where we're going to get into things that are different from the homogeneous example we did last example. So here we're looking at the Laplace transform of the second derivative plus 6 times the Laplace transform of the first derivative plus 5 times the regular old Laplace transform of your solution y. Then when you take the Laplace transform of 12t, you have 12 times 1 over s minus 1. Do a quick double check, make sure I didn't mess up that formula. Then we have to build our rules for the Laplace transform of y, y prime, and y double prime. Well, the Laplace transform of y is simply capital F, not F, capital Y. The Laplace transform of the first derivative is s times your capital Y minus 1 of your initial conditions, the y of 0. Let's go ahead and plug in for this guy. We plug in for this guy, this is going to be s times capital Y minus negative 1, so plus 1. Last guy we need is your second derivative, Laplace transform of the second derivative. This guy is going to be s squared, capital Y, minus your first initial condition, I forgot the s, don't forget the s, minus no s times your second initial condition. So again, we're going to go ahead and plug in here. So we'll get s squared times capital Y minus negative 1, so that's plus s, minus the other initial condition, so that's minus 7. I'd always recommend building that where you get to plug in your initial conditions over to the side, but again, you don't have to. So when we plug in, we'll have s squared times capital Y plus s minus 7, then 6 times s times capital Y plus 1, and then 5 times capital Y. And all of that still equals 12 over s minus 1. Now, technically speaking, we can be done with step 1. So the next thing we care about is we're going to care about solving for that capital Y. So step 2, solve for our capital Y. Well, you look for everywhere there's a capital Y. Got one there, got one there, you got one there. Huh? So we've got a, and let me go ahead and actually group these guys together just because I'm being lazy. First term here, we've got an s squared. Second term here, we've got an s, but don't forget the coefficient 6 out front, so those would distribute. So we'll have a plus 6s. And last one, we have a plus 5. Now, notice we originally started with constant coefficients on all of our y terms. So notice here in these parentheses, that looks like our characteristic equation, except we used s's instead of our normal letter. Now, we have a couple of guys, a couple of terms that don't have a y in them. We have the s, we have this negative 7, we have what's really a 6. So let me show the distributing marks right there. What's really a 6. So if we add these together, this would be s minus 1. If you move them all to the other side, what happens? For s from both sides, we're going to have negative s. We have our negative 7 plus 6. Well, that's negative 1. Move it to the other side, it'll turn into plus 1. And then you've got what's already over there, the 12 over s minus 1. So notice here what happens. If you have a non-homogeneous guy, you've got stuff that moves over plus something that was already there. Not a big deal, we can deal with it, but that's what's going on here. All right, now what do we want to do? We still want to solve for capital Y, so we can totally do it. We can divide both sides by that quadratic, the s squared plus 6s plus 5. Don't actually do that. Do this instead. It'll make your life so much easier, specifically s squared plus 6s plus 5. Oh, we probably should have done parentheses, so parentheses. And here's our negative s plus 1, and here's our 12 over s minus 1. Okay. Now, you want to have all of this into one specific fraction. Why did I put it in this way instead of do everything divide by the s squared term? Just so you don't have a compound fraction where you've got this 12 over stuff, then divided by this new guy. This just makes it easier in the algebra for most people. Now, in order to get this one common fraction, I'm going to do a little trick, and the trick is some side work where I add everything inside the square brackets and make it a common, convert it into one fraction. Okay. So here's the aside. So in order to add these guys together, you have to have common denominators. So this is negative s plus 1. We want to add it to 12 over s minus 1. Well, you need the s minus 1 on the bottom. In order to force that, you're going to multiply top and bottom by s minus 1. So this means here, if we multiply that guy out, we're going to have what? That's a negative s squared. You have the other term at the end. It's a negative 1, and the middle terms are going to both be, it looks like both s's, so 2s. Then we're going to add the 12. But notice here, if you add the 12 to that guy we already have, that's really just going to be 11. Okay. Now, put this all together. This tells us that our capital Y, our Laplace transform of our solution, is going to be negative s squared plus 2s plus 11. And that's being multiplied by this guy right here. But remember, it's still got its own factor on the bottom of s minus 1. Now you can just multiply that new expression of s squared plus 6s plus 5 on the bottom. Now, one of the things you do when you deal with fractions is you want to check to see if the denominator is going to factor and turn into partial fractions, or if you're going to have to complete the square. So one of the checks to do at this stage is just sort of look ahead and see if you can factor the denominator. Our denominator is already factored with an s minus 1, so you look at that new quadratic, that s squared plus 6s plus 5, and what do you guys think? Does this thing factor? If it does, you'll have s plus something, s plus something else. So any guesses what those two numbers might be? Yep, they would be 1 and 5. In fact, the only possibilities of what they could be. So what that means is when you go ahead and multiply the denominators together for this 1 over bits times the simplified version of the fraction we had, your final answer down here would be the entire numerator. You just multiply that by 1, then s minus 1 multiplied by those two factors that I wrote in red. So this would be s plus 1, and then I did not write the 5, s plus 5. Now, that takes care of step 2. It also takes care of all of, not all, but a little bit of the hairy algebra. Technically speaking, this mess right here is a perfectly fine answer for step 2. Not useful in any way, shape, or form, but it's perfectly fine. So step 3. So here, we want to find or solve for the actual solution, which is your inverse Laplace transform of the expression we just found. So partial fractions. So we'll have negative s squared plus 2s plus 11 all over s plus 1, s plus 5, s minus 1. So this will break up into 3 fractions. I'm going to skip some of the partial fraction steps, but here's the outline. So a over s plus 1, b over s plus 5, and then c over s minus 1. To solve for these guys, you multiply by the common denominator. So you'll get negative 2s. I lie. Should definitely not write that down. I combine the first two steps. Negative s squared plus 2s plus 11. Then you'll have a times something. It'll be the two denominators that are not s plus 1. So this would be s plus 5, s minus 1. Your b would be the denominators that are the other guys. So this would be s plus 1, s plus s minus 1. I lie a little bit. If you have repeated factors, you have to make sure you're multiplying by whatever you need to build to the common denominator. And lastly, you have c. This would be times s plus 1, s plus 5. So your special guys that you'd plug in 1. That would cancel the first two terms. You'd be able to solve for c. Plug in negative 1. That would cancel the last two terms. You'd be able to solve for a. And plug in negative 5. It would cancel the first and last terms. You'd be able to solve for b. And I'm totally just going to give you what a, b, and c actually equal. So here, A, so extra work. A, which is over S plus 1, is going to be negative 1. B, which is over S plus 5, is also going to be negative 1. And C, which is over S minus 1, is going to be positive 1. And when I built this guy, I can't remember if I pulled it from the book, but if I didn't, totally built it first from this guy and then worked backwards is how you actually build these questions. That way you get nice answers instead of just randomness. So what this tells us is, I'm going to plug in. This tells us that the fraction we care about is the same as, and I'm going to reorder it, 1 over S minus 1 minus 1 over S plus 5 minus 1 over S plus 1. Notice I swapped the first and the last fraction only so we didn't have a leading negative. No, you don't need to do that. So here's what we actually care about. Our solution y is the inverse Laplace transform of negative s squared plus 2s plus 11, all divided by s plus 1, s plus 5, s minus 1. And what we just found was that internal fraction is the same as 1 over s minus 1 minus 1 over, and I'm going to go back to the original way because I want to point something out. So the original way, if we plugged in a equals negative 1 to the first fraction, would be negative 1 over s plus 1, then negative 1 over s plus 5, and then 1 over s minus 1. So that was what I was trying to avoid before. I was trying to avoid the negative on the first one. Oh, well. So if we go ahead and solve this guy, notice all of them are going to turn into e's. The first one would be negative e raised to the negative 1. The second one would be negative e raised to the negative 5. And the last one would be e raised to the t. And if you go back to the original differential equation, here's the thing that I wanted to point out. See if we can actually see back to the original guy. Okay, so it's not letting me show you guys what the original one is. I can't zoom, apparently, out that far. All right, so if we go back to the original differential equation, one of the things that you would be able to spot is this first guy actually turns out to be your associated homogeneous differential equation. And this third one right here turns out to be your particular solution. And if you'd used method of undetermined coefficients, you would have used your characteristic equation to grab these first two, and you would have guessed to be able to figure out that second part. This Laplace transform stuff does all of it together. But that would be the idea of what goes on when you have not equal 0. In other words, the non-homogeneous differential equations, which is what we're mainly going to focus on. Okay? So I've got several more examples, but I think we've got time for one more today, and then we'll do the rest of the examples next time. So the next example that I've got for us is one of the examples that Laplace transforms are totally geared to handle. It's an example that we cannot use method of undetermined coefficients on, and we also can't use variation of parameter on. And as I'm writing down this example, see if you can spot what's in this differential equation that makes it so we can't use any of our other previous methods that we had. And it's still an initial value problem, so our initial conditions are 0 and 1. Anybody spot what about this guy makes it so that you cannot actually use variation of parameters or method of undetermined coefficients? And while you guys are thinking about that, I'm going to write down the same formulas for the Laplace transforms of our derivatives, since we're going to need them. I don't have any guesses yet. So here's the issue. discontinuous function. But it turns out your method of undetermined coefficients, you have to have the constant coefficients. We're totally fine there. We could totally find the y with a subscript h. We could find the general solution of the associated homogeneous differential equation. What we couldn't do is we couldn't deal with the guess because we don't know how to deal with this discontinuous function. Same deal happens with variation of parameters. Technically speaking, you could probably deal with it a little bit, but you'd have to do some fanciness in terms of your integrals. So in terms of what we've been doing, this one doesn't work so well with your variation of parameters either. And if you look into the nitty-gritty details of your formulas for variation of parameters, one of the stipulations is that it's actually a continuous function. So you'd have some extra issues going on there too. Okay. So turns out the Laplace transforms, when we deal with them, no problem. We know Laplace transforms, or we have Laplace transforms of our step function. Okay? So we're going to do the same thing that we did before. First step is we're going to take the Laplace transform of both sides. So step one, take the Laplace transform of both sides. Now, I'm going to go ahead and make some of the steps go a little faster. So here, when you take the Laplace transform of the left-hand side where the y's are, this is exactly the same thing as, well, I'm going to split it up already. So this is the Laplace transform of the second derivative plus the Laplace transform of y. And we will need to go ahead and figure out the Laplace transform of our step function. Now, we go back and we grab what these guys are. I set up the formulas over here to the side, and notice here, we're not actually going to need that formula for the first derivative because we don't have a first derivative, so no worries there. We already have that Laplace transform of y, the solution, no change there. It's just going to turn into capital Y just as a placeholder. Some people prefer to keep it in the symbol. I wouldn't recommend it. It's so much extra to write, but up to you. You could leave it in either form. Formula for the Laplace transform of the second derivative, which we actually do have, we're going to plug in 0 for the first initial condition. That means that term with the s disappears. And when we plug in 1 for the value of the first derivative of y with respect to 0, you'll have the subtract 1 at the end. So when we plug in over here, we'll have s squared capital Y minus 1. And then we'll add that to a copy of capital Y. Now we just have to grab the Laplace transform of that discontinuous function. And remember the rule for the Laplace transform of the step function. This guy was totally e to the negative as all over s. So we just have to figure out what RA is. Did anybody grab what RA is? Yep, RA is 3. So this turns out to be e to the negative 3s over s. Now, next step, what do? We're going to go ahead and solve for that capital Y. Step 2, solve for capital Y. Now we have two capital Y's right there and right there. So when we solve for them, there's going to be an s squared times capital Y and a 1 times capital Y. We'll just go ahead and factor that capital Y out. Notice one term does not have a Y in it, so we'll add that 1 to both sides of the equation. All right, so next step, get regular old Y, or really capital Y. So we're going to have 1 over s squared plus 1, and then we're going to have e to the negative 3s over, I just need to push that up, over s times s squared plus 1. In this case, we're not actually going to combine these guys together into a single fraction. Why? Because they're already in two different fractions. They're decently nice forms for taking inverse Laplace transforms. So we're not going to do that trick of combining into a single fraction, like one of the few times when you wouldn't do that. So step 3. Find or solve for your actual solution, which is the inverse Laplace transform of what we just grabbed. So little y, or if you prefer, what often people will do is they'll do little y of t to indicate that you're going back to t's, or you're going back to your actual solution. Now I'm going to do the same trick here that we did before when we were dealing with discontinuous functions. I went ahead and pulled that e raised to the negative 3s out front. Now note, this guy is totally the same thing as calculating the inverse Laplace transform of s squared plus 1, and then calculating the inverse Laplace transform of our e to the negative 3s times 1 over s squared plus 1. First guy is a relatively straightforward guy. So let me actually not put the equals quite that close. So for this first guy right here, anybody have a guess what's going to happen to him? Or what function it's going to turn into? Yep, it's totally going to turn into sine. And the key thing with sine is we need to know what the k is. Anybody spot what k is? K is always the square root of the thing being added to the s squared. So in our case, it's just going to be 1. Easiest one we've had so far with sine. Now, the second inverse Laplace transform has a e right here. So that means we're going to have a copy of our step function ut minus a. We just have to figure out what a is. Anybody grab what a is there? Don't ever think it. It's actually 3 again. So put this all together, and we're going to have sine of t plus u times t for the step function. And then we have to figure out what the inverse Laplace transform is of 1 over s times s squared plus 1. I was trying to be a plus 1. But you swap the t with a t minus a, and our a was 3, so t minus 3. So there is a little bit of work here, and specifically we're going to need to do partial fractions to break that expression up. I'm just going to tell you what it breaks up into. So this part right here are 1 over s times s squared plus 1. That guy turns out to be something over s plus something over s squared. And it turns out it's going to be 1 over s plus minus s over s squared. So if we go ahead and find the inverse Laplace transform of that guy, we'll have 1 over s minus s over s squared. Anybody have a guess what that's going to turn into? Well, the first guy, 1 over s, is just going to turn into 1. And the second guy of s over s squared plus 1, that's going to turn into cosine. So this would be minus cosine of t, where here our k would be 1 again, just like it was with the sign up top. So put this all together. This is the answer that we need to plug into the bracket. It's right here multiplying by their step function, except wait a second, no it's not. Everywhere there's a t, we're going to go ahead and replace it with t minus a, or t minus 3. So when we go ahead and put this in, we'll have 1 minus cosine of t minus 3. And bam, that right there would be your final answer. So notice here what's going on. This guy, we've got our sine, we've got our cosine, like what you would expect to start seeing if you were looking at your characteristic equation with the associated homogeneous differential equation. Specifically, it was originally second derivative of y plus 1, so that turns into imaginary roots from your characteristic equation. But then you have this adjustment with this step function right here, and that is totally how the non-homogeneous part from the original differential equations was taken care of. Okay? It's sort of adjusted over here. Okay? So you now have an example of homogeneous, not homogeneous, and somebody with a discontinuous non-homogeneous part.